Hi everyone, a very warm welcome to this session where we will be discussing particle core model. Particle core model has several aspects, but today we will be focusing on a mismatched CW beam propagation in a periodic lattice with linear transverse focusing. So let us jump into it. For our convenience and a systematic approach, I have divided this session in three different sections. So we start with the conceptual details, and that will lay down the foundation for our discussion, followed by the mathematical treatment, where we will obtain the governing equations, and finally we'll solve these equations numerically and see the results in the final section of our video. So let us go ahead with our first section, that's the conceptual details. So as I mentioned, we are talking about a mismatched CW beam. Okay, the beam that we have chosen here is axisymmetric, so x and y dimensions are same. Also, the beam is uniform in nature. So if you look here, this is the xx prime plane, this is yy prime plane, these are phase space plots, and this is xy coordinate. All right, so if you will notice, the number of particles throughout this beam that I have shown here in all three planes are constant. So now I hope it's clear that we are taking a CW beam, so we are considering only transverse direction, and we do not consider any longitudinal effect right now. So it's a long cylinder of charged particles. Also, this long cylinder is uniformly occupied with the charged particles. All right, it means the number of particles per unit cube is constant. So, now this beam will be injected into a periodic lattice with transverse linear focusing force. One of the periods of the periodic lattice that I have chosen is shown here. All right, as you can see, I have a drift followed by a focusing solenoid. This solenoid focuses the beam in the transverse direction, and finally again a drift. So there are three elements here in our period, and there will be several such periods forming our lattice. All right, so we want to inject this beam to this lattice, but before we do that, there are a couple of things that we have to take care of. The first thing that we have to do is we have to calculate the input matched parameter for this lattice or for this period. That's the first step. The next step is to obtain a beam twist parameters such that it satisfies the input twist parameter at the entrance of this period. This process is called matching. So we may not go in a great detail about what matching is and how it is performed, but briefly I would like to show you what happens when you have a matched beam and when you don't have a matched beam. So alright, so here I have taken 5 periods of the lattice that I have chosen. So see, there is a drift, there is a solenoid, there is a drift, and that forms one period, and I have 5 such periods here. And so if we calculate the input matched parameter for this period, this lattice, and we rotate the phase space of my beam such that it satisfies the input matched parameter at this point, that is at the input of my lattice, then you will observe that the beam will be periodic with respect to these periods. What I mean by that is the twist parameter here, that is at the input of the first period, is as same as twist parameter at the input of the second period and third period and fourth period and so on and so forth. So this is the case when you have a matched beam. So beam is well behaved, oscillating with the frequency of my period. Alright, so this is the beam envelope. Alright, now what happens when we don't have a matched beam? So let's see that as well. Again, we have same 5 periods of our lattice, and now we are introducing a beam mismatch of 50%. So if you do that, and if you see my beam envelope, you will find out the twist parameter here and here are very different. First hand, you can look at the beam radius, and you can see they are very different, and that leads to difference in beta values. Similarly, if you try to plot the x prime, you'll observe the same. So when you don't have a matched beam, the beam will perform certain kind of oscillation and will have some wavelength, but that will not correspond to the period of our lattice. Alright, and since I am showing you only 5 periods, this behavior looks systematic, but if you consider multiple periods like say 50 or 100, this behavior itself changes along the lattice. So I hope now it is clear what happens when you have a matched beam or when you don't have a matched beam. Okay, so in general, ideally we would prefer to match the beam before we inject it into a given lattice. Alright, so now I hope this is clear. Now let us look at some more consideration of the model. So given a CW beam, if we take any particle in the beam core, it will experience only two kinds of forces. First, the space charge forces. That's because we have a beam of charged particles, so they'll exert space charge forces on the particle. And second force is the external focusing force, and in our case that will be because of the solenoid that we have taken. So there are only two forces acting on the particle. The next consideration is we do not consider any particle-particle interaction in our system right now, so no collisions. We consider the interaction of a particle with the beam core. That's it. Now, as I mentioned earlier, we are considering a uniform cylindrical CW beam. So we neglect the longitudinal direction for the moment, and if you take a uniform cylindrical CW beam of charged particles, you already know that the space charge forces within the beam or within the cylinder is linear in R and goes as 1 over R as you are crossing or as you go out of the core. Now finally, the particle or the particles in the beam cannot influence the envelope trajectory, alright, or the core trajectory. The core in fact can play a vital role in determining the particle motion, but a particle cannot affect the core motion, and this is the final consideration that we have for this model. Now briefly, let me tell you briefly what we want to do here. So here our primary objective is to study the oscillation of the uniform core, that is the beam that we have injected in our periodic lattice, but in the presence of an initial mismatch. So we have a beam, we are injecting it with an initial mismatch in a periodic lattice, and we want to study its interaction with the particles in the beam core or in the beam. So this is the This is the primary aim of the whole session that we are going to cover today. Now, if it is clear, then you will easily understand that there are three types of oscillations in the system. First, matched beam oscillation. As I showed you in earlier animation, that the beam oscillate even if it is matched with the period that correspond to the period of the lattice. Now, when you introduce a mismatch, then also the beam oscillates, but with a different wavelength. And the third type of oscillation that we have in our system is the oscillation of the particles, because particles are also facing forces, and that will lead to their oscillations, and in general what we call them betatron oscillations, and it will have a different wavelength than these two oscillations. So there are three types of oscillation in our system. So I hope it's clear. Now let me show you how a matched beam behaves in a long periodic lattice that I have chosen for the current discussion. So I have chosen the periodic lattice with a total length of 180 meters, and one of the periods that I have already shown, that corresponds a drift, a solenoid, and a drift. Now as you can see how well behaved the beam is. It's oscillating with a single frequency, and that I'll be showing you soon, and with a constant amplitude. So this is a well behaved envelope, so to say. Now let us see what happens when we introduce an initial mismatch. Also please note that this value of R that we have chosen here, or that we have calculated here, is called the matched beam radius, and later we'll be talking about it when we will be dealing with the equation governing these motions. Alright, but please note that this radius is what we call matched beam radius. Alright, so now let's see what happens when you do not have a beam with a matched beam radius in this lattice, and if we introduce a beam mismatch of say 50%, that's the case that I showed you earlier. So I'll be showing you now the animation that demonstrates the propagation of a mismatched beam in the lattice that we have chosen with an initial mismatch of 50%. Now, as you can see, if we have an initial mismatch of 50%, the beam behaves in a different way than what we observed with the matched condition. So it's very clear from the plot qualitatively that there are two types of oscillation that we can observe. There are these oscillations with shorter wavelengths, and they are as same as the oscillations that we observed with the matched beam. In addition, there are these oscillations, okay, with a longer wavelength and shorter frequency, alright, and they are the oscillations that was introduced because of the initial mismatch that we have given in the system. So whenever we provide an initial mismatch, that will lead to introduction of an extra additional mode of oscillation in the envelope. Okay, so now you see the difference what happens when you mismatch the beam. You will land up with an extra mode of oscillation in the envelope. For the moment, please remember only this much, and I'll be comparing the two cases simultaneously soon. Alright. So to start with, we talked about this matched beam oscillations, and that was well behaved and with a constant amplitude with the same frequency. The third type of oscillation that I discussed was this particle oscillation, and these are the particles that forms this envelope. Now if you see, these particle oscillations have different oscillation frequency altogether. It do not match with the oscillation frequency that we observe for the matched beam envelope. So even with the mismatch case, where we have two different frequencies for the envelope oscillation, that is one that corresponds to the matched envelope frequency, and the other that is introduced because of an initial mismatch that we have provided. These particular frequencies are different than both these frequencies. All right, and they are the two systems that we are going to study. So in order to quantify these oscillations, what we can do, we can take a first Fourier transform of these oscillations, that's my particle oscillation, and my matched envelope oscillation. So we can take four FFTs basically. First, FFT of the matched beam envelope oscillation. Next, FFT of the particles oscillation in the matched beam. The third one is the FFT of a mismatched beam envelope. And finally, the FFT of the particles in the case where we have an initial mismatch. So this plot here shows the FFT of the matched beam envelope and mismatched beam envelope. This yellow plot shows the FFT of a matched beam envelope, and that's why I have kept the color same so that you can make it out. And this plot here shows the FFT of the mismatched beam envelope. So you can see it very clearly that in both these cases you have this peak that's common, and that corresponds to the oscillation frequency that we have here and that we have here after these oscillation dies down. Okay, in the case of the mismatched beam, as we expect, we have an additional mode of oscillation, that's because of mismatch, and that leads to a lower frequency or higher wavelength. So as soon as you introduce a mismatch, you will land up with another peak in frequency domain. So, but what happens to these particles? Do we observe difference in frequency in these two cases as well? Let's see what happens. So here I have plotted only 5 particles, and here also I have plotted only 5 particles, because if I plot all of them, it will be pretty crowded and we won't be able to make out anything. And now if you look at this figure, this is the FFT of the particle oscillation in the case of a matched beam envelope. That's these particles, and it's very clear that they have a definite peaks here, but though they are different for every particle, they have different frequencies, but the peak is pretty sharp. Now as soon as you introduce a mismatch, these particle frequencies also changes, the oscillation frequency for these particles, and that is demonstrated in this figure. As soon as you introduce an initial mismatch, the particles are gonna have different frequencies. There's a introduction of frequency spread in the particles. So if you take particle A, particle B, particle C and D, in the case of a matched beam, they had frequency peaks that were coinciding with each other, but now they have shift in frequency. So since I have plotted only 5 particles, it's very difficult to see it here. But if you do these calculations and plot multiple particles, say 1,000, 10,000, or 1 million particles, you can clearly see that the spread in frequency in the case of mismatched beam particle oscillation increases. So this is where we are quantifying these oscillations. So I hope it is clear what's happening when we are moving from this scenario where we have a matched beam to this scenario where we have a mismatched beam. Alright, so let us go to simple physics, and if we don't look it from the point of view of accelerator physics, let's look at them from the point of view of simple oscillations. So you'll see there are two types of oscillations here: the particle oscillation and the envelope oscillation. As one of our considerations demands that these particle oscillations cannot affect these on envelope oscillations, but this envelope oscillation can influence my particle oscillation. Alright, so consider a case when you have a simple pendulum and with a constant length, fixed length, and you are apart from the oscillation of simple pendulum, you are oscillating the pivot of the pendulum in the vertical direction with a different frequency, say omega, from the natural frequency of oscillation of the pendulum, say omega naught. Okay, now in this case, if the external frequency, that's omega, is twice of the natural frequency of the oscillation of the simple pendulum, that's omega naught, then a resonance condition occurs and the amplitude of oscillation of the simple pendulum increases exponentially. This is called parametric resonance, and the condition can be obtained using Matthew's equation. And if you want, we can discuss that. Please put a comment below, and we'll get another session with that. All right, so that's the part, that's basically the idea here. We are trying to understand the resonances between the particle oscillation and the envelope oscillation, because if the resonance condition between them is satisfied, the amplitude of these particle oscillations will grow exponentially and they'll form beam halo. Moreover, since these oscillations are non-linear, the frequency of oscillation is a function of amplitude of oscillation. So as the amplitude increases, the frequency changes, and after some time the resonance condition is not at all satisfied, and therefore the amplitude starts decreasing. So the nonlinear force is somehow playing a role in limiting the formation of beam halos here. Okay, so the nonlinear force causes the halo formation, and also it limits the halo formation. So I hope it is clear, and this is as far as the conceptual section, the conceptual part of the discussion is concerned. And now we will be going through the mathematical treatment of the talk. All right, so let us now look at the mathematical equations governing these oscillations. So there is an envelope oscillation and there is a particle oscillation. So first we will be looking at motion of our envelope, and we will be using famous KV envelope equation for that. So just for the sake of completeness, I would like to introduce these terms to you. This R is the beam radius, that's a function of the Z, that is my propagation direction. This K naught is my structure phase advance, or it basically is indicative of external focusing force on the system, or it's the oscillation frequency of the envelope, alright, in the absence of space charge forces. Now again, this K here, capital K, is my generalized perviance, and this generalized perviance is a function of is linear function of beam current. So higher the current, higher this value. So this term indicates space charge forces, and that's why we have a negative sign here. As I told you, this term focuses the beam, and that's why we have a plus here, and this term defocuses the beam, and that's why we have a minus here. So this generalized perviance again is a function of beta, gamma. They are relativistic factors, and this epsilon naught is absolute permittivity, that's constant. Mass of species is constant for a chosen species. C is the speed of light. C is speed of light. Alright, so if you change your beta gamma, the perviance changes, and if you change your beam current, the perviance changes. Now the final term is the term that's because of the emittance in the beam. And simple word, emittance is a measure of thermal energy in the beam, alright, intrinsic thermal energy, or more qualitatively it's the phase space area without pi. But in practice it's very difficult to calculate area. So if you want to quantify this emittance looking at phase space area, and if your ellipse is tilted, it's very difficult to calculate it. So normally we take RMS emittance, because it's easy to calculate. You have a distribution of particle, you just calculate the second moment of the distribution in a given phase space plane, say xx prime or yy prime or whatever you want. Alright, so that's my emittance term. Again, emittance leads to defocusing of the beam, and that's why we have a negative sign here. So I hope it is clear. So in the next step, so if you remember in our earlier slides, I talked about a term matched beam radius. So we are given an envelope equation. We want to calculate what should be my matched beam radius such that the beam will oscillate with the periodicity of my period that I have chosen in our lattice. So for that we consider a smooth approximation where we assume that if we take a matched beam, the variation in R with respect to Z goes to 0. So in order to calculate the matched beam radius, and we'll call it, we'll denote it by R naught, we assume that dr dz is equal to 0. Now if we assume that and we substitute that here, we will be left with k naught square R minus k over R minus epsilon square over R cube is equal to 0. Now you just simplify this equation and by multiplying throughout by R cube. So we will get k naught square R4 because there was R already, minus k R square because R was here, R cube gives you R square, and minus epsilon square because there is R cube here. Now this equation is quadratic in R square, so and we can get the solution of form R square is equal to k plus under root k square plus 4 k naught square epsilon square over 2 k naught square. And this is a solution. This is my matched beam radius square value. Now we can just simplify it further with the notation u, that is defined as capital K over 2 epsilon k naught, and we can write this as epsilon over k naught u square plus 1 plus u square, and this you can verify. Alright, it's pretty easy to verify. We just take k outside and epsilon and over k naught. So basically k is there, k naught is here. You take epsilon outside, 1 over epsilon. All right. So and it's very easy to verify this that we can write the whole expression using definition of u like this. Fine. Now for sure, if the beam is not matched, R will have dr dz would be 0, and R will perform oscillation, and those oscillations are the one that I showed you in case of a mismatched beam. All right. So we looked at the envelope equation, and now look at the particle equation. For simplicity, we are considering only the x direction. For y direction, similar approach follows. Okay. So we have a second derivative of x with respect to z plus k naught square, the same k naught that we had for the envelope oscillations, x minus fsc. This term is the space charge force term. Alright, is equal to 0. So as I mentioned earlier, fsc is linear in R as long as you are within the core, and goes as 1 over R as soon as you are out of the core, and that condition is mentioned here. Alright, so it's k over x over R square. Alright, This is basically r naught square, r square. This r is the envelope radius, and x is the transverse direction coordinate for the particle. So if your x is less than r, it goes as x. If x is greater than or equal to r, it goes as 1 over x. Alright, so we have two equations now in hand, the envelope equation and the particle equation. Now in the next step, we would like to define certain parameters in order to make our equations dimensionless. So to start with, we'll define small r, that is equal to capital R over r naught. This r naught is my matched beam radius. This r is my initial mismatch, so it denotes initial mismatch. Alright, so and we'll be looking at oscillation of this r, okay, along the lattice. Now please note that if I do not introduce any mismatch, this r is equal to r naught, and the value of r is equal to 1. And suppose if I have a mismatch of say 0.5, so this r will be 0.5 r naught, and we'll get r is equal to 0.5. Now small x, okay, that's equal to capital X, that's the beam x coordinate over r naught. Alright, next parameter that we define is eta, that is equal to k over k naught. I'll come to small k in a moment. Alright, and finally we defined a variable tau that is equal to k naught z, so it's basically representing the z coordinate. Now about k. Now k is a net focusing force on the particle, actually, or okay, and that includes the space charge force, all right, and the external focusing force, okay, within the core, and it is given by k is equal to k naught square. This represents the external focusing force minus kp square over 2. So kp is a plasma wave number, but since we don't want to discuss plasma wave number right now, we'll write kp in terms of my generalized permeance. So that will give me k naught square minus k over r naught square. So this is the external focusing force because of the magnetic field that we are using here, using our solenoid, and minus a space charge term, okay, that defocuses the beam. We simplify it further, so we write small k is equal to under root k naught square minus k over r naught square. Okay, that makes sense, right? Now please note that with these terms we can modify our envelope equation. Alright, so what we will do, we had envelope equation, and let me show you. So we had this envelope equation. Now we don't want r, we want r by r naught, and that's what we are going to do. So we are going to write this whole equation in terms of small r, eta, small r and eta basically, and k naught and other terms will be absorbed in the new definitions that we have defined just now. Alright, so we use envelope equation, we'll write r by r naught, and to compensate this we have r naught here, and this this z dz will be substituted by tau, and that's why we have a k naught square here, because tau is k naught z. You calculate d tau dz from here. Alright, so that's why we get k naught square here, plus k naught square r that was already there, and we have r naught here just to get small r, minus again k over r was there, we have r naught here again to get small r, minus epsilon square over r cube was there, and we have r naught cube, you know, again to get small r cube. Okay, we do that. Now what we have to do is we just have to put r over r naught is equal to r. Okay, so that's what we get here. We have r cube, but still we are left with k naught square r naught here, k naught square r naught here, r naught here, and r naught cube here. Alright, So we will divide throughout by k naught square r naught. So there won't be anything here. K naught square r naught will go from here as well, and here you will be left with k naught square r naught, and there was already r naught, so r naught square and small r minus epsilon square over k naught square. All right, and r naught will give you r naught 4, and this is r cube. So this is the expression that we have, right? But please remember, we have defined eta is equal to k over k naught, and that was equal to 1 over k naught square minus k over r naught square. That's what we calculated earlier, right? And if you take k naught outside, so k naught square outside, you'll get this term is equal to 1 minus, because there's a k naught already there, and they'll cancel, and you'll get k over r naught square k naught square, because you're taking this k naught square outside. You'll be left with 1 k naught square here as well, right? And this is so this is eta, and k over r naught square k naught square is equal to 1 minus eta square. You basically square this eta here, so you will be you can get rid of the square root. This eta square comes here, so you will be left with 1 minus eta square, and on the LHS you will be left with this term, k over r naught square k naught square. All right, so now you get 1 minus eta square is equal to k, capital K over r naught square k naught square. Please note that in my envelope equation we have the same term here, capital K over r naught square k naught square. So we will substitute this term by 1 minus eta square. So that's what we are doing here. Then we are left with d2r over dz d tau square plus r minus 1 minus eta square, that comes from here, over r, that was r here, from r comes from here, minus epsilon square over k naught square r naught 4 r cube. So there's no change here right now. All right. We have this envelope equations, and we have substituted 1 minus eta square here. So but still we are left with epsilon square k naught square and r naught 4, all right, and we want to write this as well in terms of eta. Now please note that eta can also be written as 1 plus u square under root minus u, and this we can verify by substituting the value of u that we wrote earlier, where we, in the definition of r naught square, where r naught square was equal to epsilon over k naught u plus under root 1 plus u square. All right, so we can use this definition of this r naught square, and where we have epsilon over k naught 1 plus u square under root plus u. All right, so we take this and we multiply the whole thing with 1 plus u whole square under root minus u, and 1 plus u whole square 1 plus u square under root minus u, all right, divided by this term and multiply with the same term. Now it's basically a plus b and a minus b, so you will get this term square. It's 1 plus u square under root ka whole square, so this root goes, plus u square, all right, sorry, minus u square. So there's a plus u square minus u square here, and so you'll be left with only 1. Okay, so this term remains as it is. All right, please note that this term is basically eta. All right, so we'll get r naught square is equal to epsilon over k naught, that comes from here. This term goes to 1, and this whole term is basically eta. So, and if we take square of this term, so we'll get epsilon square over k naught square eta square, okay, is equal to r naught raised to 4, right? So that's why we have epsilon square over r naught 4 is equal to k naught square eta square. You have epsilon square over r naught 4 here. That will give me k naught square eta square. So we get k naught square here, eta square here, divided by k naught square r cube. So k naught square from here and from here cancels, and we'll be left with an eta square term divided by r cube term. Alright. So we substitute it here, and finally we'll get d2r over dt square plus r minus 1 minus eta square over r minus eta square over r cube is equal to 0. And this is my normalized or dimensionless envelope equation that we arrived at. Alright. Similarly, we have to perform similar steps for particle motion, right? And let's see how we do it. Now, if you remember, we have d2 capital X over dz square plus k naught square x minus fsc is equal to 0, and this is my equation of motion of particles. Now, fsc, as we already discussed, is linear within the boundaries of the beam core and goes as 1 over x outside the beam core. All right, and we have defined x is equal to capital X over r naught. So similar, so we don't want x here, we want small x here. So we want we want derivative with respect to tau, that is equal to k naught z. So we get k naught square d tau square here, and since we want small x here, we divide it by this term by r naught and multiply it with r naught. So that's why r naught here and small x here, plus k naught square, again small x, r naught because we multiply and divide this capital X by r naught. So capital X by r naught will give me small x, and one r naught is left. Now we have kx over r naught r square is equal to 0. That's for x less than r. Again, we just have substituted, multiplied it and divided by r naught. Okay, and we get small x, and r naught is left because of the r naught that we had in denominator. All right. Now for capital X greater than the core radius, the term changes. The changes that occurs only in the last term, and as you can see, we have similar terms: r naught k naught square d2x over d tau square plus k naught square x r naught minus k over x r naught, because now the force is 1 over x. All right. So again, we just want d2x over d tau square, so we divide the whole equation with r naught k naught square for both cases when x is less than r and x is greater than or equal to r. Alright, and we get d2x over d tau square plus x, because k naught square x will be taken away, minus kx over again k naught. There was already an r naught here, so r naught square rs square, right, is equal to 0. And similarly for x greater than r actually. Alright, please note that again this we already derived, that capital K over k naught square r naught square is equal to 1 minus eta square r naught square k naught square. So we'll get d2x over d tau square plus x minus 1 minus eta square over x, alright, is equal to 0 for this term, and a similar substitution will work here. So we will get 1 minus eta square here as well. So let's see what happens when we make the substitutions. Alright, so we'll get d2x over d tau square plus x minus, as I said, 1 minus eta square we substitute in where we have capital K over r naught square k naught square. We'll get 1 minus eta square x over r square. That's for x when the particle is within the core. And we'll get a similar term, that d2x over d tau square plus x minus 1 minus eta square over x is equal to 0 when the particle is outside the core. Alright, so So let's see the final equations that we have for our envelope and the particles. So let us look at the final expressions that we arrived at. For envelope, we have d2r over d tau square plus r minus 1 minus theta square over r minus theta square over r cube. And for particles, we have d2x over d tau square plus x minus 1 minus theta square x over r square is equal to 0 for x less than r, that's a particle within the core, and d2x over d tau square plus x minus 1 minus theta square over x is equal to 0 for particle that's outside the core. So it's basically goes as 1 over x here and goes as x here. Alright, so this concludes the section on the mathematical treatment, because finally we have arrived at the two equations that governs the motion of my envelope. Okay, so basically the motion of the mismatched radius, and it will tell me how it evolves along this lattice, and the equation of the motion of the particles, that is when it is within the core and when it's outside the core. As you can see, it's a coupled equation, and we can solve it numerically using several algorithms that's available, and that we will be discussing soon. Not the algorithm, but what kind of algorithms are possible to use to solve these equations. Alright. Okay. Finally, we will be going to look at the numerical solutions of the equations that we arrived at in the while deriving the equation of motion of envelope and the particles. Alright. So let us go ahead. So if you remember, these are the two or three equations that we have. One for equation of motion of the mismatched radius, that's small r, and these two equations are for particle evolution when the particle is within the core and when the particle is outside the core. Now we can solve these equations numerically, and in order to do that, as you might be aware, that we have to convert this second order differential equation into two first order differential equations, and similarly these two equations, that they are of second order, to two first order differential equations. So basically these two equations are for the particle. The only problem is you have to solve them in different regimes. By regime, I mean for a reason where when the particle is within the core and when the particle is outside the core, and this you can do very easily by using a if condition in the loop. Alright, so these equations can be solved using several algorithms. You can use Euler, Leapfrog, Runge-Kutta, and Boris-Pusher. So, but I would advise you to use Euler. It's less time taking, and if you use symplectic Euler, I may not go in detail of using how to implement these algorithms. If you want, please put a comment in the comment section below, and I'll discuss each of them or one of them in upcoming videos. Alright, so we can use these methods and land up with solutions. Okay. Alright, so by solution I mean we want x, that's a particle position. This x is basically r over r naught. There's a particle position with as a function of tau, that's k naught z. Envelope, mismatched beam envelope radius as a function of tau. Alright, and this is r by r naught. I'm sorry, this is capital R by r naught, not small r by r naught. Alright. Then the next thing, if you remember, we have defined T as dr d tau, that's the divergence of this mismatched beam envelope. So this is my T, and U is basically particle divergence, alright, with respect to the propagation direction, that's k naught z. Here tau is k naught z. Alright, so you can see that we have a particle position, envelope radius, alright, the divergence of the envelope for the mismatched envelope, and the divergence of the particle. Now using these four parameters, what all we can do? So we can look at envelope evolution along the propagation axis, that by plotting r as a function of tau, alright, you can look at particle phase space by plotting x and u, alright. We can also look at particle evolution along propagation axis by plotting x versus tau. And finally, we can look at envelope phase space by plotting r and t. So before I go ahead, let me give you a brief introduction to the to different reason of the Poincare plot that we can use in order to analyze the dynamics of the envelope and particles. See, we have divided this plot schematic in three major regions. The first region is the central part, and that denotes the contribution from the core particle. The next one is this part, this region, and both of them are symmetrically aligned with respect to the central part, and they represent the tail particle oscillations. Alright, and finally this region, that's big region, and that surrounds my tail particle and the core particle, is formed by the halo particle in the beam. Alright, so if you observe these kind of oscillations that surrounds both the tail particle and the halo particle, the tail particle and the core particle, that will be our halo particle. So with this in mind, let us look at the solutions that we obtained for the differential equation that we arrived at. So as I mentioned earlier, the solution that we get from the differential equation are in terms of small r, that is the ratio of capital R over R naught, and that tells me the envelope mismatched envelope oscillation, and that is plotted in yellow here in the first figure. And the oscillation, the evolution of the particles, that is small x over R naught, is plotted in red here. So that was the first thing that we mentioned, right? That we can study the evolution of particle and envelope along the propagation axis from those solutions. Alright, the next thing that we could study was the phase space, like x prime and small x prime and small r prime. Alright, so this is what is plotted in figure 2. And as I mentioned while explaining the Poincare plot, that there are several regions. So there is a core region, there are tail particle regions, and there are halo regions. Alright, so we can clearly see three different regions here. But here I have plotted the x prime and r prime at every calculation point, okay, along the lattice. But what we can do, we can plot a Poincare plot. And how do we do that? We try to locate the minima of this envelope oscillation, and at every minima we'll plot the value of the particle oscillation. Alright, so at every minima, that's minima of r, small r, we plot x on x-axis. Alright, and similarly at the same point we also plot x prime. So that's what we have plotted here. Alright, so here also you can see different regions. There's a core region, there's a tail particle region, and there'll be halo region around this, right? Finally, here I am showing the tune for the envelope, mismatched envelope, that is in yellow, and the tune of these particles. Okay. Now, if you notice, all these four plots, okay, are for a given value of eta, and in our equation eta represents my tune depression, right? That's the ratio of the of k and k naught, small k and k naught, where k naught is structure phase advance and k represents a focusing force that comes from the contribution from the space charge forces and the magnetic field that is focusing the beam, right? So it is basically tune depression. So what we do, we change the value of eta and try to see how my envelope, mismatched envelope, and these particle oscillations will change. Similar effects we can observe using phase space plot, Poincare plot, or tune plot. Please note that one can have different kind of interpretation, can analyze the situation in a different way, and here I'm just showing you a solution that one can obtain using any one of the numerical techniques that I mentioned, and can have these kind of perspective to look at those results. So we won't be concluding anything here, but you can just see how these oscillations changes, the particle oscillation frequency changes as you change your eta values, and that you can see here, alright, in this plot, because as frequency changes you'll find a change in the FFT peaks here for the particles and for the envelope as well. Also, if you want, you can also look at this plot, Poincare plot, and see for what value of eta the particles, most of the particles are forming this core region or the tail region or the halo region of the Poincare plot. Alright, so let me start this animation and enjoy. So couple of things that I would like to point out. As you can see, with change in eta value, the peak for the envelope, mismatched envelope oscillation doesn't change, so frequency remains same for the envelope. Alright. On the other hand, the region occupied by the particle in Poincare plot changes. Like right now it forms the core region and the mostly it forms the core region and the halo region. Okay, and as you see, as eta changes, the density in different region changes. All right. Also, I would like to point out there are different kind of oscillation frequency that is introduced because of eta. There was already these oscillations. All right. There's a betatron oscillation, but now you have another oscillation here, and that's because of the space charge force. You can analyze it further, but for the moment, as you can see, as my space charge forces goes to 0, that oscillation dies down. Okay, and please note that that oscillation was not the oscillation that we observed for the mismatch mode. Okay, that's a different oscillation, and that's because of the space charge forces. All right. For the moment, from my side, this is all what it is right now, and please let me know if you want to have more discussions. I'll be happy to do that. Thanks very much for your time.